All right, Chapter 2, Section 5. Here we go. There are 4 objectives. The first one, use the rational zero theorem to find possible rational zeros. It sounds complicated. It might even look complicated on this slide. I promise you it's really not that bad. So here's an example. It says list all possible rational zeros of this function. So you have a third-degree polynomial. And really, what you're going to find is the most important part to identify is the constant at the end, the -2, and the leading coefficient, the 15. Those are the 2 most important parts of the polynomial when you're focusing on this objective. So what you're going to do is to list all of the factors of the constant term up here in the numerator. So the constant term was -2. So all of the factors of -2 are positive and -1 and positive and -2. Those go up into our numerator. Our denominator are going to be the factors of the leading coefficient. And so factors of our leading coefficient, which we said was 15, the factors are 1, 3, 5, 15. We're always throwing plus or minus in front of all of these. So the possible rational zeros are going to come from dividing each number in the numerator by each number in the denominator. So here is that ultimate list right here of possible rational zeros. These 2 answers, or I guess I should say these 4, because you have positive and negative versions of each. In the blue, you'll see it says divide plus or minus 1 and plus or minus 2 by plus or minus 1. So those came from taking each of these numerators, plus or minus 1 and plus or minus 2, and dividing by plus or minus 1. If you divide by plus or minus 1 for each of these, you get exactly what you had before. The next 2, these 2, come from taking each of the numerators and dividing by plus or minus 3. This pair comes from taking plus or minus 1 and plus or minus 2 and dividing by 5. And the last one comes from taking plus or minus 1 and plus or minus 2 and dividing by 15. So there are 16 possibilities right here of rational zeros. So if you were to graph this thing, basically this is what we're talking about. If you were to graph this thing, this graph could possibly pass through the x-axis at any of these locations. And so on the next slide, you're going to see actually where it does pass through. So let's go take a look. So I just used Desmos and copy and pasted it into this slide, but here it is, the exact same function. And you can see that it does pass through -1. That was on our list of possible rational zeros. Here it passes through what looks to be -1/3. And here it looks like it's passing through 2/5. Obviously the -1 is easier to distinguish. However, there are 3 total times that it does pass through the x-axis at rational values. And so all 3 of those are in this list. So that is the first objective. Use the rational zero theorem to find possible rational zeros. Clearly this entire list is not every single one of these. No. Did that graph pass through every single one of these numbers? Absolutely not. However, when it passed through the x-axis, did it pass through at these values? Yes, it did. So you found the possible rational zeros. It will always come from this list if it's a rational zero that it passes through. Okay, moving on to the second objective. This slide might look a little bit chaotic. I'm going to draw a little bit on this screen here so you can see what we're focusing on first, second, and third, but the objective is to find zeros of a polynomial function. So we're going to build off of what we just did on that last screen as well. So here we go. The first thing we're going to focus on is right here. The second thing we're going to focus on is right here. And the third thing we are going to focus on is right here. Those numbers are going to disappear in a second as I use the cursor to highlight what exactly we are going for here. So let's see. Let's get rid of that. Okay, so again, the objective is to find zeros of a polynomial function. Here's the polynomial function we're dealing with, x cubed plus 2x squared minus 5x minus 6. And so we go through the last objective. We start by using our last objective to list the potential or possible rational zeros. Here's the list of 8 possible rational zeros. Now to find out which ones actually are, because all 8 of them will not be, we want to know, does one of them work? Does 2 of them work? Does 3 of them work? Or do 3 of them work? Which ones? How do we know? So here's what you do. You start by picking the number 1 and you use synthetic division. The 1 goes in the magic box over here. I like to call it the magic box. We use the coefficients and the constant to set up our synthetic division. And here we get a remainder of -8. When you get a remainder of -8, that means that the 1 is not a rational zero. It's not going to be an x-intercept of this function. So we move on, and you could try -1. You know, the test 1 did not work out over here. Test 2, you know, most of us, I would say, probably would prefer to use positive values rather than negative, so let's move on and try +2. That goes in our magic box. We use synthetic division, and bingo, we find out that that last value there is 0. That means that our remainder is 0, and that must mean that 2 is a solution, or a root, or an x-intercept. It's all the same thing. So that's a huge plus for us, and we know that we can rewrite the original polynomial. Here's the original polynomial. When you're asked to find zeros, you set the polynomial equal to 0, and we now know that if 2 is a solution, that x minus 2 must be a factor, and we're left with, if you go back here and look, 1x squared plus 4x plus 3. So here it is, right next to my cursor. There are those 2 factors, x minus 2 times x squared plus 4x plus 3. Bingo. The good news is that x squared plus 4x plus 3 can also be factored nicely and quickly into x plus 3, x plus 1, and so now at this step we have 3 factors whose product is 0, so one of those factors has to be equal to 0. So either x is 2, x is -3, or x is -1. Bingo, we just found the zeros of the polynomial function. Now I might have gone through that slide a little bit quickly, but for instance, let's say you're confused with the synthetic division. Well, feel free to go back and look at any of our previous videos where we focus in on how to do synthetic division. I think that's a benefit, that you can always go back and look at those old videos that we've done to make sure that if you need to brush up on something, you can. So that is our second objective. Moving on to objective 3. Solving polynomial equations. Now this slide again has quite a bit of information, and ultimately our answer is going to be down here next to the cursor. The problem is starting up here. So it's very similar to what we just did on the last slide. However, this time it's a 4th degree polynomial, and we are going to introduce technology to show you how beneficial it can be to help you in this process. So x to the 4th minus 6x squared minus 8x plus 24 equals 0. We could create our list of possible rational zeros by using the constant term, the 24, and the leading coefficient of 1, and writing out a whole list and then trying synthetic division. But instead, we are going to plug this into our graphing calculators and take a look at what the graph looks like. So here's a window shot of what the graph looks like, and you can see that it appears that the x-intercept is going to be 2. And so we're not going to just eyeball it and take it for what it's worth here. We're going to actually go and then use synthetic division to make sure that it actually does give us a remainder of 0, which means that it absolutely is a solution or a root or an x-intercept. And you can see that when you do use 2 up there in that magic box, you do in fact get a remainder of 0. So that means, I'm going to go right up top here, that means that if 2 is in the magic box, that means that x minus 2 is a factor, and then the remaining piece here, and again, if we go back and think about our synthetic division, the 0, the last number, is always the remainder, so that means -12 is the constant term. -2 is the linear term, that's the one that gets the x attached to it. This 2 would be our quadratic term, that gets the x squared, this would be our cubic term, which gets our x cubed. So up here we have the two factors, x minus 2 and x cubed plus 2x squared minus 2x minus 12. The product of those two things gives us the original polynomial that we were dealing with. However, we need to continue factoring. Now check this out. When you go back and look at your graph over here, you'll notice that, now this goes back to one of our first sections in chapter 2, where you learned about multiplicity. You can see here that the graph comes down and boom, bounces off the x-axis. It does not crash through, it bounces. So that means that x minus 2 has a multiplicity that is even if it bounces and turns up. And so if it has a multiplicity that's even, that means there must be an additional factor of x minus 2. So up here next to the cursor, you'll see you have one factor of x minus 2. But now we're going to go ahead and as we try to factor just this part over here, we're going to continue factoring. This one doesn't factor anymore. It's a linear factor. We're done. Over here, however, we do have more work to do, so we know that x minus 2 is also going to be a factor of that. So we stick 2 in the magic box again, and we use the coefficients of x cubed, which is 1, x squared, which is 2, x, which is negative 2, and the constant term, negative 12. And sure enough, you'll see down here that the remainder is 0. So by using the technology, the graphing calculator, we've identified that x minus 2 is a factor twice, and so here's our original polynomial. Here's the one we had at the top of the screen. And then we continued factoring. We said, hey, you know what? X minus 2 is a factor twice. And when you did that, you had 1x squared plus 4x plus 6 as one of the factors. So now we have it written out down here as 3 factors. X minus 2, and x squared plus 4x plus 6 equals 0. What would be phenomenal now is if the x squared plus 4x plus 6 was easily factorable. However, it's not. We would have to resort to using the quadratic formula to factor this part, to solve this part. So at this point, I would say, okay, we have 3 factors listed whose product is 0. So that means either x minus 2 equals 0, x minus 2 equals 0, that gives you the same solution, or x squared plus 4x plus 6 equals 0. So you'd have to use the quadratic formula to solve this part. I did not include that in this slide. However, when you do use the quadratic formula to solve that, you will get the answer to the left of the cursor, which is negative 2 plus or minus I root 2. That is not a real solution. And so down here, the final result of this, it says the solution set of the original equation is 2, which happens to be a solution twice, and negative 2 minus I root 2 and minus 2 plus I root 2. And a graphing utility does not reveal the 2 imaginary roots. So at the start of this problem, when I said, hey, let's check out use the graphing technology to see where it crosses the x-axis, you may have thought, oh, wonderful, this will tell us where all of the answers are. It doesn't, unfortunately, because if we scrolled out and looked at the entire function, the only place it touches the x-axis is at the number 2, and you can see down here you have some imaginary solutions, which shows that you do not cross the x-axis again at those locations. So there is our third objective. We're going to go and hit our fourth objective on this last slide. Here it is. Use the linear factorization theorem to find polynomials with given roots. And I have an example here. A lot of writing, but here's the problem. It says find a 4th degree polynomial. That just means that when you're done with this problem, the leading term is going to have an x to the 4th. And so if you look down really quickly, here's the end result, and you can see that the leading term does have x to the 4th involved in it. So find a 4th degree polynomial function with real coefficients that have or has negative 2, 2, and I as zeros. So they're telling you that the polynomial function that they're looking for you to create will cross the x-axis or have a solution at negative 2. It will also cross the x-axis at 2, And then it has this imaginary solution of I. We'll dig into this part in just a little bit. So a fourth degree polynomial, there has to be 4 solutions to this. Now, 2 of them are real, and you have 1 imaginary that's listed. There are always an even number of imaginary solutions. There will never be 1 imaginary solution. There will never be 3 imaginary solutions. Since they give us I as one of the solutions, we also know that negative I will be another solution. And you can see written here next to the cursor, it says, because I is a 0 and the polynomial has real coefficients, the conjugate negative I must also be a 0. So even though they only gave us 3, -2, 2, and I, we immediately know that negative I must also be the 4th 0 of this polynomial. There are going to be 4. We now know what they are. So we write it in this form, which looks a little hectic. It's not something we're super comfortable with, but let's go down here. You have this A term here, and then you have x plus 2. Well, that came from, you had a solution of -2, so it goes in as a factor of x plus 2. The second one, it was a solution of 2. That goes in as a factor of x minus 2. Here you had positive I. Well, that goes in as a factor of x minus I. And then as we mentioned, there's a fourth one that wasn't mentioned up top, but it would be negative I. Well, that goes in as a factor of x plus I. So now all we need to do is multiply this whole thing out, and I promise you it's easiest to multiply out if you multiply these 2 together first, multiply these 2 together second, and get those answers, which are here, x squared minus 4 and x squared plus 1, and then multiply these 2 together, giving you this result. Now, here is where the f of 3 equals -150 part comes in. When you're here, you now look at that information up top that we hadn't looked at yet, and it's telling us that if you plug in the number 3 for x, you should get an answer of -150 for the function, or for y. And so here we go. We leave the a part and we replace each of the x's with the number 3. So instead of x to the 4th minus 3x squared minus 4, we have 3 to the 4th minus 3 times 3 squared minus 4. That has to equal -150. If you solve this and find out what a is, you're pretty much done with the problem at that point. And this goes through and shows you how you solve it for a, and when you do, you get an a value of -3. So then we just go back and plug in -3 into this a position. And so you can see here it says substituting -3 for a sub n in the formula, etc., gives you this right here. So this right here looks identical to this part, but you've just plugged in the -3 for the a term, and it says, or equivalently, it gives you this. So if you were to distribute the -3, you would get this answer. So that takes care of our 4 objectives for today, and this video is pushing the limits here. We're almost at 20 minutes. That's much longer than I'd like our videos to be, considering you probably will have to stop, pause, etc., rewind, rewatch things. This was a pretty hefty lesson, and I ask you, as always, to make sure to call me over if you're confused with anything.